Previously, on any manifold M, we have defined the notion of a Riemannian connection, which allows us to differentiate a vector field on M along another vector field on M. However, remember that our series is about not just any manifold, we care about Riemannian manifold. These are manifold equipped with a Riemannian metric. So we don't want to just look at any connection, we want to look at the connections that are actually compatible with this Riemannian metric. Well, what does it mean for the connection to be compatible with the metric? We'll give 5 different ways to express this compatibility. These are 5 equivalent conditions. But first, let us explain the intuition. Let's see, what kind of information does a Riemannian metric tell us? Well, on each tangent space, it gives us a way to measure lengths of tangent vectors. Because on each tangent space, it gives us an inner product. But as is, we cannot compare these inner products on different tangent spaces. It doesn't make sense to say that the inner product is the same or different, because these are different vector spaces. However, now, with a connection, we can actually compare these different inner products, these different lengths. Why is that? Well, because with a connection, we can define the notion of parallel, and in particular, we can define parallel transport. So we can transport this vector v0 into different tangent space. In this tangent space, this vector has another length, right? The length with respect to g at gamma t1. So we'll say that this connection and this metric they are compatible if this length is equal to this length. More formally, parallel transport between 2 points on any curve in M is an isometry. The second condition says basically the same thing. Say we parallel transport 2 vectors v and w to another tangent space, then their dot product here, their inner product here with respect to the metric g should be the same as their original inner product. Another way of phrasing it is that if v and w are parallel vector fields along a curve gamma, then their inner product should be constant everywhere. If we can unpack these conditions out computationally, then we'll get the condition 3 and 4, which are the product rule. Condition 3 is the product rule just for the case of vector fields along curves, and condition 4 is the product rule for any vector fields in general on M. Condition 5 follows immediately from condition 4 by computation, but we want to make a quick remark to explain what these notation mean in condition 4 and 5. You might be a bit perplexed here by this and this notation, because the connection here, we see that as we define here, it takes in its input is a pair of vector field, right? But here its second input is a function. So g of y comma z is a function, it's a smooth function instead of a vector field. And here its input is a g, a 2 tensor, instead of a vector field. So what does this mean? Well, one thing we didn't mention explicitly is that this connection, a linear connection, always have a natural extension to this tensor bundle. By extension, we implicitly mean it has to satisfy some kind of compatibility condition, which we will not list here. So we just want to say quickly, in the case of zero tensor bundle, i.e. the bundle of smooth function, this connection is very easy to define. The connection of a smooth function f in the direction of the vector field x is what we think it should be, because it should be the directional derivative, right? And so we define it to be x of f. Similarly, we can extend this to the 2 tensor, which includes g. And actually, the defining formula for this is just going to be the difference of this left and right hand side. That's why these two are immediately equivalent. Alright, so that's what it means for a connection on a Riemannian manifold to be compatible with the metric.